So this so-called paradox of motion is an interesting one to think about and introduces some interesting ideas. It's part of a longer series of a few different paradoxes that are very similar, which we can look at as well if you like. This one concerns movement, and essentially we split this movement up into halves over and over again, and we reason that motion therefore doesn't make any sense. And we'll formulate this, give this argument, and then we'll look to rationalize why this argument falls apart, because obviously we know we can move. So to get from any point A to a point B, we know that first we have to travel halfway from A to B. Okay, so that's nice and simple. So we're traveling halfway, and then from this point we then have to go halfway from that point to B again. And then from here we have to go halfway again, and then halfway again, and then these halves again. Increasingly more difficult to draw, but you can see we keep doing this infinitely many times. So the argument is if there's always another half to go, we always have to travel half the distance we have left before we can go the full distance. We have to do this infinitely many times. It's therefore impossible to ever get to the point B. So it's therefore impossible to move anywhere, and motion's impossible. Okay, so you probably walked from your bed to your laptop to watch this video, so you know for a fact that you can move, unless this is all some sort of wacky simulation. But anyway, the point being that we're going to show what's wrong with this argument now. So an argument of this form might make sense if we were saying to get from a point A to a point B, we at first have to do this chunk of distance, then we have to do this chunk of distance, then we have to do this chunk of distance, and then we have to do this chunk of distance, and then we're there. Because this is a finite sum, so we've broken up this distance into a finite sum of smaller distances, and it all adds up, and we get from A to B. That's fine, okay? So why does this argument go wrong? Because we do have to go half and then half again. That logic's not incorrect, and that's because this is an infinite sum. And infinite sums behave slightly differently to finite sums. Okay, so a finite sum of numbers always adds up to another finite number. Okay, whereas infinite sums can be a little bit tricky. It might seem that if we add up infinitely many terms in a sequence, okay, so this is what a series is. A series is a sum of terms in a sequence. If we keep adding these up forever, it might seem that we can't get a finite number, because whatever number we land on, we always add on a bit more. So it's impossible to get to a finite number, okay? But this is actually false, okay? And this is where this argument falls apart. And we'll start to see this now. We're going to rationalize why some sums do converge to finite limits without really formally proving it, but giving some pretty sophisticated mathematical reasoning. In terms of the philosophical reason why this doesn't work, I mean, that gets really complicated in terms of how you consider time and space and all those sorts of things. And if you want to Google that, then feel free. But mentally prepare yourself. But we're going to go through the mathematical argument of this finite sum, infinite sum. Okay, so say this distance from A to B is of length 1. I don't care what the units are, as long as we're working with the same units. So that could be 1 meter, that could be 1 kilometer, that could be any unit of measurement you like, 1 foot, 1 hand, whatever. Then we know that this length of 1 has to be equivalent to adding up these halves, okay? Alright, and if you take this is 1/2, half of a half, this is 1/4, this here is 1/8. So this sum, and how we represent it in summation notation, is the sum from n equals 1 up to infinity of 1 over 2 to the power of n, okay? And you can see this because n equals 1's a half, and then we're adding that to 1 over 2 to the power of 2, a quarter, 1 over 2 to the power of 3, 1/8, then we'd add a 16, so on. And the claim is, for motion to be possible, this has to be equal to 1. And we're going to justify that now, mathematically. So the way we consider the sums to infinity is we consider, what if we were working with this sum, but up to a finite number of terms. So, and then we'll find some formula for that. And then we say, what if that finite number tends to infinity? So we're going to consider the sum from n equals 1 up to k of 1 over 2 to the k. And we do know, the question is, how do we write this in terms of some formula in terms of k? And this looks very similar to, not quite in the form of a geometric sequence, only because geometric sequences tend to start from n equals 1. So I'm going to take out n equals 0. Sorry, I'm going to take out 1/2. Okay, and then I have a sum from n equals 1 up to k of 1 over, sorry, this should not be a k, this should be an n here, of 2, and I've taken out this half now, so I've got 2 to the n minus 1, and then we perform something called a change of variables. So we're going to substitute in n equals n plus 1, essentially, n minus 1, and we'll just change this to the sum from half, n equals 0 up to k of 1 over 2 to the n, okay? And now this is a geometric series with first term a is equal to 1/2, and common ratio r is equal to 1/2, because 1 over 2 to the n is equal to 1/2 to the power n. Okay, and our formula for the sum of the first k terms of a geometric sequence is given as, okay, so here's the formula for the sum of the first n terms of a geometric series. Like I said, we have a is equal to 1/2 and r is equal to 1/2, so in our case this is 1/2, 1 minus 1/2 to the power k, all over 1 minus 1/2. Okay, so then we consider what happens when k goes to infinity, and when k goes to infinity, this 1/2 goes to 0, and all these terms, the other terms, remain the same because they've got no dependence on k, they're just constants. What does it mean for the limit of 1/2 to the power k to tend to 0 as k tends to infinity? Well, that means that no matter how close you want to get to 0, okay, you can find k big enough such that you get that close, alright? Okay, so for us, the sum of the first n terms, and sorry, this should be a k here, because that's what I've chosen as my index. The sum of the first k terms as k tends to infinity, well, like I said, all these stay the same, this goes to 0, so, and I'm going to use slightly dodgy notation, you shouldn't really write this down, but I'm going to write s of infinity. Really you should write the limit as k tends to infinity of s of k, so that's equal to 1/2 over 1/2 minus 1/2, that's equal to 1/2 over 1/2, and that's equal to 1. Another very similar argument to say that adding up all these halves gives us 1 is to say that 0.9 recurring is equal to 1. And this is similar to our limiting case here. Well, what we're saying is, no matter how close you want to get to 1, okay, so you want to get within 0.00001, you can add up enough of these halves so that you get within that distance. And if you can do that for any number, Alright, that means the limit of this sum must be 1. Alright, so that's one way of thinking about it. So if your teachers ever mention that 0.9 recurrent is equal to 1, that's sort of the reasoning behind it, okay, in layman's terms. So yeah, this is an interesting idea. There's a lot of these sort of fun mathematical paradoxes, and where if at first glance, maybe when these ideas are introduced, you're a bit like, what's going on here? But if you break it down a little bit, you can explain what goes wrong in the argument. So yeah, we'll be covering more sort of flawed mathematical arguments, and also fun ideas like this going forward. If you've got any suggestions, let me know in the comments. Also, if you had any questions about this video, bits you didn't understand, bits I didn't explain very well, let me know. I'll try clear it up in the comments. Yeah, or if you think I got anything wrong in this video as well, because I'm by no means perfect at maths, so yeah, that's fine too. So thank you very much for watching this video. I hope to see you in the next one. Have a good day.